Okay, welcome to this video here for Chem 161, where we'll be looking at some additional materials here for Chapter 3. We'll be touching on comparison briefly between the Borh model for the atom and the quantum model, which is the most successful model for describing the atom. And ultimately looking at the ideas behind quantum numbers to describe the identity of an electron. Okay, so in the Borh model, we had the concept that there was a nucleus and certain allowed orbits were allowed given the wave-like properties of that electron. So in other words, only a certain circumference or a certain radius was allowed for this orbit because a wave had to be had to fit perfectly onto this orbit to allow that wave to be what we call standing. So that is the beginning and the end of it link up like we just saw in my wave-like drawing around that circle. So the nearest orbit that would be allowed would be the first orbit. The next one that would be allowed would be the second. And then we would have the third. And we saw through the Rydberg calculation and equation that we could determine the relative energies of these levels. And that electrons would be allowed to transition from higher energy levels down to lower energy levels and would emit a photon if they did so. And we could also have the idea of an incoming photon striking an electron, allowing it to be promoted up to a higher energy level. So this leads to the concept of the absorbance of a photon, h nu, or the emission of a photon, h nu, and the difference between the energy levels of the orbit n equals 1, 2, 3, or 4, etc. gives us some ideas about the wavelengths and frequency and ultimately the energy, of course, of that photon. Okay, the quantum mechanics model is going to look quite a bit different. So let's see if we can organize our thoughts on that in the form of a table. So we'll comment on what's known about energy in the model, the electron, the position and path or path, so of that electron. And we'll talk about what it means to distinguish and what elements it works for. Okay, so there's some of the categories for our table, and we want to consider this for the Borh model, as we've just seen here, and compare that to the more successful model, which is this quantum mechanics model. Okay, so quantum mechanics. So in the first sort of category, we know that only certain energies are allowed and the Rydberg calculation told us that. So the energy of the n equals 1 can be calculated from that n value equal to 1 and the Rydberg constant. We have that same idea in this quantum mechanics model. Okay, so that part translates nicely between the two models. Only certain energies are allowed there. Okay, what about the description of the electron? So in the Borh model, as we have in the diagram above, that electron is still modeled as a particle on an orbit. So this Bohr model still thinks of the electron as a particle. In the quantum mechanical model, we adopt the ideas that because the electron is so small and so light, that it has both wave and particle type properties. Okay, so we've got some work to do to evolve our model to show that the electron can exist only as a wave and not have any particle concepts in this model in certain cases. Okay, and then position and path. So we have in the Bohr model that there are fixed distances reflected in the diagram above. Okay, so fixed distances from the nucleus in distinct orbits. In the quantum mechanical model, we have the idea that there is no definite position and only probabilities. Okay, so that is to say, in the quantum mechanical model, we only have the ability to predict a likely spot for where the electron is according to a wave calculation and ultimately a calculation that respects the Heisenberg uncertainty principle, that because the electron is so small and moving so quickly that we have difficulty pinpointing the exact position if we know its speed, or we don't know its trajectory, its pathway, if we know its position. So we're respecting the Heisenberg uncertainty principle in the quantum mechanical model for position and pathway information of this electron. Okay, and lastly, in the Bohr model, as far as the elements that it applies to, the Bohr model only predicts properties and data for the hydrogen model, for the hydrogen element. So not only that, hydrogen and just one electron. Okay, so we're talking about just one element from the periodic table with the fewest number of electrons. When you remind yourself of how many elements we have on the periodic table, well above 110 elements, we need something better to describe all those other elements. The quantum mechanical model works for all these others, these more complex atoms, where we have more electrons and clearly larger atoms associated with the larger nuclei with greater proton count within the nucleus. Okay, so to just briefly touch on the most important kind of new idea here, we have this concept of a wave particle type property that we need and no definite position as we build in ideas from the Heisenberg uncertainty principle. So as your textbook kind of indicates, the quantum mechanical model can give us probabilities of finding an electron near the nucleus. And so if the nucleus is positioned at the origin of our three-dimensional Cartesian coordinate system, where we say have x, y, and z to locate the sort of x direction, the y direction, and the z direction of 3D space, we put the origin and the nucleus right on top of that origin. What the quantum mechanical model allows us to do is do calculations. How likely can I find the electron at some distance away from the nucleus? And so the probability of finding the electron at certain energy levels, say n equals 1, is greatest near the nucleus, as we might expect. And as we kind of build out distance away from that nucleus, we see fewer results for where that electron can exist. So what I'm developing here on the screen is a model where I have ultimately very unlikely locations for the electrons reflected by the density of dots, and increasing kind of dot count as I go closer to the nucleus. So this is giving the idea that at some point I'm confident that most of the most likely spot for the electron is within a certain volume in this 3D space. And we typically define this as a 99% likelihood of finding the electron. And this is helping us understand the sort of electron's range as we respect the Heisenberg uncertainty principle and a 99% likelihood of finding it somewhere near the nucleus. So we cut off at 99 because technically as we go to 99.999, etc., we can start to find the electron even a little bit further. And so we can never achieve 100% certainty of finding the electron because of the Heisenberg uncertainty principle. Okay, so this sort of probability map of finding the electron as a three-dimensional wave centered at the nucleus is all for a situation where we have, for example, an n equals 1 case that we see adapted from the Borh model. We were allowed to understand the energy level described by an n equals 1, as we see up near the nearest orbit near the nucleus. We see vastly different probability functions and maps for where that electron can exist as a wave as we move to different orbital situations. So ultimately the n equals 1 case kind of looks spherical like I just cartooned. N equals 2 case, we start to see new shapes develop, and still one that's spherical, not shown here in this little figure in our upper corner. And in n equals 3, we'll see a new set develop further, and we'll see a set of these blue kind of waves in three-dimensional structure around the XYZ, and still have some of the former 2 present. And so the idea of what the electron looks like as this cloud around this, centered around the nucleus, which is of course on the Cartesian coordinate system origin, starts to look much different than this particle of an electron circulating on an orbit. Okay, so this is a tough concept, and if you're struggling with this, please reach out to me or revisit your notes from your textbook, which might help you think of this with other terms. Okay, because an electron is going to adapt different shapes and forms and have different energy levels in this quantum mechanical model, we need some additional information to help us pinpoint or assign a set of coordinates, if you will, for what that electron looks like. So just like we have for the address for a house, we have information like 1, 2, 3, 4, state, street in Bellingham, Washington. We have 4 bits of information here that from left to right increase in kind of range or territories. So the 1, 2, 3 house number is the smallest detail in the address. Then we have the street, which is a little larger. And then we have the city, which is even larger still. And then, of course, we have the state, which is even larger still. We're going to have those same kind of 4 bits of information to help us pinpoint an electron. So in the concept of quantum numbers, that feed into the quantum mechanical model and Schrödinger equation to help us describe the likelihood of finding an electron and evolve those shapes we saw in the previous slide, things like spheres or dumbbells or double dumbbell shapes for the electrons, as we see here and here. We're going to need numbers to help us assign those waveforms and refer to them according to a sort of number system. Okay, so we're going to have 4 numbers. Okay, we'll start with n, as we're allowed to adopt this from the Borh model. And so this is the principal quantum number. And this is, as we saw, this determines most of the energy of the electron. Okay. So by the Rydberg equation, we saw that n equals 1 positioned the electron at the lowest energy level, and an n value of 2 positioned the electron at a higher energy level. We see that same idea here in the quantum mechanical model. And this is, of course, reflected in the first value, n, the principal quantum number. Okay, the next one, I'll just shade this differently so you can kind of see that it's clearly a different topic, is going to be L. This is what we call the angular momentum quantum number. Okay. And as we alluded to on the previous slide, the minute we went to a different n value, some new L values are going to be allowed, and that's going to allow for us to see a new shape in the probability maps for finding the electron. Okay, so the shape of the orbital, that is the 3D wave of that electron, is reflected here through this number. Okay, so this angular momentum number determines the type of orbital and that is to say the shape. Okay. The next quantum number is going to be m sub L. Okay, so that's an italics L in the subscript position. M sub L is the magnetic quantum number. And this magnetic quantum number is going to help us determine the direction of the orbital. Okay. So in other words, to help us, we'll rewind just a moment. The direction of the orbital, if we take a look here at this area here, you can see that the orbital shape is the same in either option, but we've oriented the orbital in a different way. In one case, it lies along the x dimension. In another case, it lies along the z dimension. In the last case, it lies along the y dimension. And so this is where we take advantage and specify which direction the orbital is oriented. And the magnetic quantum number m sub l specifies for that option. Okay. The last quantum number is the m sub s quantum number. And this is the spin quantum number. And we'll see that the spin quantum number is only going to be allowed two values, one of two options. And so this one will be kind of the easiest one for us to determine when we work through permutations and options. Okay, so key takeaways at this point are that our quantum mechanical model is the more successful model. We've built off previous models, adopting the Borh model and the idea that the energy of the electron is quantized, and that's reflected through the option 1, 2, 3, or 4. Those options ultimately become our principal quantum number, n, out of one of the four options. Okay, so we still have that idea. And the new ideas where we evolve away from a particle-only situation for the electron to incorporate more ideas about wave forms and respecting the Heisenberg uncertainty principle that we can't specify exactly where the electron is. We have now the concept of an orbital, which is the 99% likelihood of finding the electron within this orbital volume. That orbital volume can range in shape and in size, and that depends both on the principal quantum number and the L value, and ultimately the direction of that orbital versus other options is set by the m sub L option. So all these ideas kind of an orbital and a probability map and shape for the electron's three-dimensional structure help us understand the position and path ideas for this electron now. And this system works for all elements from the periodic table, regardless of the number of electrons.